Right, so here is a quick introduction to Bentley Multiframe. It's a basic structural analysis and design package that's really aimed at skeletal structures like steel portal frames and so on. So when you fire it up, you start with a blank screen and you can generate buildings quite quickly. So if we click on the generate button, it's generating a 3D portal. It puts in some values by default. So we'll have one bay, and let's have two frames. Our frame spacing is going to be, let's say, 6 meters. Column height is 5 meters. Let's say we're having a pin-based portal frame column. So it's tall and skinny. Let's select all our members. We need to give each of our members a section type and a section material. So pick our section material. We'll go for steel of grade 300. And let's pick our section type. Let's go for a UB and we'll go for a 610-101. So if you want to see a 3D rendition of that, those nice big chunky sections, and we wouldn't normally have eaves beams and apex beams as such large members. So let's select those and change the section type. So it's more likely to be, let's say, tube. Let's do a 150 by 150 by 5 tube in there. So that's our basic frame. We need to apply some loads to it. So you click on the loading button. And so you can load it by a member or you can load it by a joint. So let's just say we've got a global distributed load uniformly, and we'll call it direction down. We'll call it 2 kilometers projected vertically down, and similarly another global distributed load of 2 kilometers there. And that's load case 1. Maybe you want to change the name of that load case. So you can edit the load case and give it a different name. Let's call it dead. Loading type, I'm going to call it permanent, and it's going to be used for strength and serviceability purposes. You can add another load case. Let's call it another static load. Let's call it live. And this time we're going to put in some patches. So let's go back to our frame generation picture and we'll look at the basics. Let's switch on things like the naming of each member and the numbering of each member, and maybe want to put on the name and number of each of the joints. So we can rename, I'll give a label to our bases, and let's call it base. And we can give a name to our knees. A label, let's call it knee. And to our apex, we'll give it a label as apex. And we need to define some load patches. So these are your load patches. So I can develop load patches by clicking on these buttons here. So I can do there to there. That's one load patch or one load panel, and plug it from there to there. So I've got 2 load panels. Let me save. We'll call it test 2. Save. We can fill in those details should we so wish. Let's go back to our loading. We're looking at live load. We've got no loads on at the moment, so we can say, let's say it's a roof load. So you've got a global panel load, and we'll call it 0.5. in there. So that's vertically down. And we go back to our dead load. We can add on a dead load into there with a load panel loading, and it's going to be minus 0.3 kPa applied vertically downwards. No, that's not what we wanted. Undo it. Apply a global panel load vertically down. That's 0.3. Okay, and now we can add a load case. Let's call it, it's going to be a wind load case, but we're going to do a static version of that. We'll just call it wind. And we'll apply the wind load of the local panel. And it's going to be uplift, and we're going to call it 0.8 kPa up one. And the second panel load is going to be downwards, and we're going to call it a 0.2. So that's our basic loading. At the moment, everything is rigid, so it should happily analyze it. Once you've analyzed, you can go to the analysis results. Here we have it for wind, we have it for live, and we have it for dead. We could, of course, do some combined load cases. So go back to our loading, and we add a static combined. Let's call it ULS1. So we have 1.2 dead, 1.5 live. Okay, that's going to be for strength primarily. Click OK. Then we can add another load case, a static combined, and we call it ULS2. And we've got a 0.9 and a wind of 1. So it's going to be for strength. Let's go for that. And will it have done it? If you go to your results, it needs analyzing again. So we go analyze, linear, and hey presto, we've got that. So what you'll find is you've actually got moments on the ends of these sections. So if you double click, you get a little bit of a moment, and the reason you've got that is because you didn't release it. So go back and release. Make it pin-ended. Now if I analyze it, it will say I've got unrestrained degrees of freedom. Do I want to continue? No, I don't. And the reason you've got that is you've now got a mechanism on plan. There's nothing restraining it. So let's add some more bracing elements. And let's go back to our frame analysis generator. And we can switch off the panels so we can get a better look. And then we can add on some bracing. Okay. Need to give these a member material, call it 250 steel, and we need to give it a section type, and we're going to use a solid bar. (16mm) diameter in there. So as you know, these bars really can't take tension, so you need to change the member type to a tension only member type. Will it work now? If I analyze it, it's likely to give me an error. Yeah, the reason it's giving me an error is because it's still floppy about the eaves. And because of there's no vertical bracing. So let's do the same for the vertical bracing. Join the dots. Similarly here and here. Let's give it a member material by selecting a member material 50, and let's give it a section type 16mm round, and also determine that the member type is going to be tension only member. Right, so when you analyze it, you now get this extra option, is do you want to ignore the tension or compression only elements effect? Don't tick that, because that will allow you to put compression in your tension members, these little bars. So skinny bars are not good at taking compression, they'll just buckle out of the way. So we want to keep those in. So now we can go into our analysis results, and now our ties do not have moments at the end of them. So if you suspect, if you're getting moments where you're not expecting it, you've probably got too many constraints in your model. Go back to the parent view. So you can look through the analysis results. We're starting with bending moments, shear, axial load, and then of course deflections. So look at the dead load deflections and the numbers. If you zoom in on them, you'll find out what they are. So those are the diagrams. If you go to the results, you will see here are the displacements for dead load. Let's move to ULS 1 or even ULS 2 and look at the displacements you're getting. Remember, these are factored loads, but the displacements nevertheless are quite small. Look at the reactions. Again, there are your reactions for that particular load case, and you have your output in terms of axial load and shear in two directions plus torsion, minor axis bending, and major axis bending for these elements. So we can see that our column has 3 kilonewtons on one side and 7 kilonewton meters on the other side. We haven't given the label to our bracing, so we could add that later. There are two buttons. There's member actions and there's max actions. So the member actions are actually the member actions at the joints. So hence you're given a reference joint. So that is the axial load in that member number 1 at joint number 1. To get the maximum action in the member, you have to click on the max actions table, and that will give you the axial load, the maximum and minimum axial load for that member under that load condition. So we're looking at the load combination ULS2. That's member number 1. It gives you 3 values. So we've got minus 2.55, and which means it's in tension. And then you've got a bending moment of 7 about the major axis, 0, almost nothing about the y-axis. And here are the deflections along the length of the member. And to check all that, you can look at the diagram, select member number 1, and it gives you, in this case, it gives you the deflections. But you can look at the shear, axial loads, shear forces, bending moments for that particular member. And another trick you can do is grab this line and move it across. And that tells you on your left-hand side the maximum moments at that particular point, until you get right over to the side where your maximum moment corresponds with the position you're doing it. So as you move to the left, in this case, your moment is shrinking down to 0 because you've got a pinned base. To get back to the parent, right click, go back to the parent view. You do a nonlinear. And so you can do a P delta effect and spit that out. And now we have 2 lots of analyses. So when you look at the bottom diagram, you'll see you've got the notation that it's P delta. in here. And again, if you look at the results, this is for P delta. If you want to compare it with the first order analysis, you simply click on the linear versus non-linear results. So that gives me the first order analysis. Click it once and it gives you the second order analysis. Okay, and that's the analysis side of things.